Hello. Happy what is it? Monday? Happy Monday. So I'm sorry I couldn't be online um last week, but I think we'll have plenty of time between today and also Wednesday. Now that we don't have lab, we'll do this. So at 4 p.m. on Wednesday, we can talk a little bit more. If you have questions regarding anything, you can drop them in the chat or you can send them over Discord as usual. So I assume you've read the message and you've heard from Harper that we are no longer having in-person labs this semester. It's kind of sad. It was nice to get to see everybody, but I'm glad we got most of the labs done. We got the biodiesel analysis done. We missed a couple in there, but we should be fine. And with the adding of the at-home experiments that you've been doing, that should be all the labs that we need to do this semester. But I know it was the kind of the best part of the class for a lot of you, not just me. So it is sad that we don't get to do that anymore. All right, so today I wanted to kind of go through the stuff for the week, and also note that the way this is set up, everything is set to be due on the 22nd, which is Sunday night, just to be consistent. But really, I wanted to give you that Thanksgiving week just sort of off, or if people had some old stuff to catch up on, you could use that. But realistically, you can do all this stuff through that week as well. I just didn't want to, have everything due the Sunday of the break and then kind of have your break all full of doing work. So it's due the 22nd, but I'm going to put a note on there also that just says, if you want to take Thanksgiving week to do it, also that's fine. It's not going to be late. And speaking of that week, since we're all going to be home and not traveling and all that, you may have some time. So if you want to go back and catch up on other stuff from earlier in the semester, you're always welcome to do that. These deadlines were meant as guidelines so that stuff didn't pile up as we went through the semester, and to keep us on track so that we knew what we were talking about. But if you missed some of those assignments, some of those worksheets, some lab write-ups, things like that, you can still submit those and still get credit for those. So if you have a little bit of extra time this week or next week, please do that. All right, so today we're going to look at the biodiesel analysis again. We did the calculation parts. Now I want to look at the rest of it. If you are still unclear on those calculations, then let me know and we can go through it again either tonight or Wednesday. And then we will look at the other part as well. Sorry, I'm trying to make sure I'm getting the messages that are coming in too. And then also the other part for this week is talking about greenhouse gases and the chemistry of that greenhouse effect. So we will, and which will kind of get us into global warming as well. So we'll talk about that a little bit tonight, or if it's getting too late, we'll move that to Wednesday. All right. So first you'll find this week the biodiesel analysis folder again in module activities, where it was before. And everybody finished your analysis, which was great. Everybody got good calorimetry data that you'll be able to do your calculations with and calculate your yields. And again, you can follow step by step through those calculations in a previous video that was linked in the activities folder. Again, to remind you, it's this thing here, the biodiesel project final analysis, that you want to follow. And this is what you'll be submitting for that final project. And again, I have the date set as this Sunday, but you may also take next week to work on this if you would like. But if you get it done by Sunday, then you've got some time to relax and just kind of regroup before finals and all that start coming up. So that is up. I'll leave that up to you. All right. So last time we talked about some of these calculations, particularly 2, 3, and then the heat of calorimetry below. So today I want to look at specifically number 1, which is kind of the big one, besides the calculations, did you produce it? How do you know if you actually produced it? And how can you use the tests that we did in lab in the analysis to prove that? All right. So let's look at, and then we'll look at a couple of these other ones as well. All right. So first, how do we know if we produced biodiesel? So the main thing you want to look at here is the results from your analysis tests. So let's go through them again if you don't remember from lab. First, you had a wash test, and that is a measure of how well the biodiesel separates from water. If the biodiesel is pretty pure, it should separate from water quite well. So when you shook it up with the water, it would kind of look all homogeneous for a second, but then it should settle out quite quickly. If it took a while, like minutes or something, to really make clear layers, then that's an indication that there are some other impurities in there that are acting as what's called surfactants and kind of binding those biodiesel and water layers together. So you can look at that. What that doesn't tell us, though, is the purity necessarily of the biodiesel with respect to the oil that you started with. So we all started with oil in that experiment. And the other thing that could happen is that your oil didn't react all the way. You know, we were pretty limited on time. If you remember way back to the beginning there, you had to kind of get everything in there. You had to wait for it to come up to temperature. You had to wait for the sodium hydroxide to dissolve in the methanol. And then when all that finally was ready, you could dump it in, and then we had to react for the hour. And so there's a chance that the oil didn't all get reacted. And so the second test you did, the methanol test, is a good indication of whether or not there's leftover oil, because that starting oil is not soluble in methanol. So when you tried to dissolve it in methanol, if you looked at the very bottom of the container, if you saw any little tiny droplets, or if it looked cloudy at all, that's indication that there was leftover oil in the biodiesel. And that would not have come out in the wash test, in that first test, because the oil also separates quickly from the water. So you'd really need the methanol test for that. All right. And then the other way that you can identify it, is through the GCMS data. Now, I don't have that posted yet. It just came back, but we did get it for everybody. And so I will be posting that. I'll show you where I'm posting it, and I'll show you how to go through it using this old data. So I'm going to put it in this folder here, GCMS data. Right now, all we see is some old data in there, because, like I said, I just got the new data back, and I will post that. But let's just pull up one of these old ones so I can show you what this is and what's actually happening. Because when we were in lab, we didn't really have a chance to talk about what GCMS is and what we learned from it. All right. So first, it's worth your while, I think, just to look up a basic explanation online of what GCMS is. Gas chromatography, mass spectrometry. You don't need to get into all the details of the experiment or the instrument design, but it's an interesting piece of equipment. It's not just used in chemistry labs. It's used in all kinds of stuff, from airport screenings to drug screenings, things like that. So it's a neat instrument to know about. But basically what we're doing, we did paper chromatography earlier in the semester, where you let the inks and the dyes kind of run up the paper and separate. And what we're going to do here is, or what we're doing here is also called chromatography, because it's separating the molecules out. So I put your sample of your biodiesel in this instrument, and it went through this really long tube that was filled with a special kind of material that some molecules bind more strongly to than others. And then it kind of made its way through this big tube, which is coiled up in the machine. And as each molecule made it out, it went into something called a mass spectrometer, which is kind of a way of weighing a molecule and then breaking it apart into pieces to see how it is structured. We'll keep it at that. So what you get out is you get a couple pieces of information. First, you get this graph, and this one from 2017 looks pretty different from what yours looked like. Probably we were starting with a different type of oil, and that's why. But some of the same results. So the thing to focus on here is the x-axis, right down here. This is time. So it's actually time in minutes. So what this is telling us is that, at about 10.44 minutes, this molecule, whatever this is, came out of the instrument and led to this signal. And then what's this big giant one? 11.4 minutes, this next thing came out of the instrument and was measured, and so on. And then it looks like the last thing to come out was like around 13.1, or these little ones kind of behind me that aren't even labeled with a time. The height of the peaks don't really matter, but if we take the area under the peak, like how much space the peak takes up, that actually correlates to the amount of that molecule in the sample. So we might guess here that this big giant peak that's also kind of fat is the majority of whatever is in there, whatever that molecule is, and then this is a little bit less and maybe a little bit less. Again, it doesn't correlate directly with height, but it's the overall size, the area under the peak, also known as the integration, that gives us that information. So all this part tells us, this is the gas chromatograph, and this just tells us there were some things, there were some different molecules, they went through the instrument, they came out at different times. We can then use the mass spectrometry part to figure out what those molecules are. So if we go down to the next part, you'll see this library search report. And you get this interesting readout here. So I'm going to go through what these tables mean and how we can use this to understand what is in our biodiesel. All right, so peak number is just like a number that's assigned to the peaks, 1 through whatever, however many peaks the software finds. Then the next column is RT, which stands for retention time. So if you saw these numbers that were on top of the peaks before, that's the time that it takes for that particular molecule to get through the instrument. So we're just saying, okay, this one was the one at 10.33, this is the one at 10.44, this is the one at 11.40, and so on. Then the next column is area percent, and that is how much area under the peak as a percentage of all the peaks. So this gives us a sense of how much, what percent of the overall sample is a particular molecule. So you can see this peak number 1, pretty small, just 0.65%. Peak number 2 is a little bit more substantial, 8.36%. Peak number 3 was that big, tall, fat one at 81.98%. So that's going to be the majority of our sample is made up of this. And then the library thing here, library/ID, is the software's attempt to analyze the spectrum and match what type of molecule it is. And the reason, so for each of these peaks, it gives 3 choices. And then if we skip way over to the right here, this qual column is a measure of how well it matches. Like how well it matches either a theoretical or experimental spectrum. So we can see here that like it's basically saying all 3 of these molecules are possibly it, but the best match is these first 2, which are essentially not indistinguishable. And then same thing for the next one. So we've got this different molecule, and we've got either a 98 or a 96% match. In general, you can go with just the top one. Sometimes there's a collection of molecules that are indistinguishable from each other, like in this peak number 3. All 3 of these have a 99% match, which means the instrument just can't tell which one it is. They're all very similar molecules, and so this is just something that this instrument can't distinguish in this particular way. In other cases, it's a little more clear cut, like down here, you've got 3 choices, but the bottom one is down at 60% compared to 87 or 99, so it's a pretty good chance that it's actually this first one in this case. And the more unique a molecule is, the better chance that it can figure it out. But for our purposes, all we want to know is, are these things biodiesel molecules, or are they something else unrelated to biodiesel? So to do that, we have to think a little bit about what the reaction is, what we did, and then how we, and then what these molecules are. So I don't expect you to know just from these names what these molecules are, but we can look them up in and look for a chemical structure, and then compare that to what we know from the last video about what our biodiesel molecules look like. So let's try it. I'm just going to pick one that's easy to type in because I can't seem to copy paste from here. So octadecanoic acid methyl ester. So you can't see that on the top of my screen, but I'm just typing that in because I just want to know, what is that molecule? What does it look like? And it looks like it keeps coming up as a different molecule. So like octadecanoic acid methyl ester, but it also seems to come up as stearic acid methyl ester. And it turns out those are actually the same thing. But let's just take a look at the molecule itself. Okay, wow, that's really small. I'm just trying to make that a little bit bigger so we can see it. So you can I mean, it definitely got a little weird here, but you can see it's a bunch of carbons with a carbon double bond oxygen and then another carbon on the end. And if you go to compare that to the biodiesel stuff from the reaction earlier, what biodiesel molecules or FAME, fatty acid methyl ester molecules look like, that is one of what they look like. So that's good evidence that that's a biodiesel molecule. And we can do that for any of the molecules in our list. I would say for the purposes of the report, you don't have to go through and look up every single molecule that shows up in the report, but take the top 3 peaks or top 4 peaks, depending on how many there are, and look those up. And if those are indeed biodiesel molecules, then there's a good chance, then you can conclude that you've pretty much made biodiesel you've made biodiesel. So hopefully that makes sense. Let me know if you're having trouble with that or if you don't quite understand what you're looking for there. I do have your actual data now, so I will post that as soon as I can. I may have to split it up into some separate files or something. It kind of comes through as some raw data, but we'll get it up there. All right, so back to the analysis then. So the tests from lab there are going to be your major comparisons here. The other one is you measured the density. So you can look up some known densities of biodiesel and compare your measured density to those densities. And then if it's similar, that can be some good evidence that you have indeed produced biodiesel. So just like anything else in science, one test doesn't generally tell you the answer you're looking for. But if every test you do gives you more and more evidence toward a specific conclusion, then taken together, it can be reasonable to say, this is my conclusion. This is what these things mean overall. All right. So speaking of those comparisons, a couple of the questions down here ask you to compare to some literature standards, and those standards are also in the biodiesel folder here, and I think I talked about this in the previous video. If you look at the fuel table down here, you can see some properties of different types of fuels. Again, the other video has a little bit more information here. So you can compare your biodiesel to what we'll call literature or known values for biodiesel, which is right here in the rightmost column. We don't have comparisons for all of these columns. Like for instance, we didn't measure the weight composition of different atoms. We didn't measure the specific gravity, although that can be related to the density. There is density here, although it's in a little bit different units, so you may have to do a little conversion there. You can look that up. We didn't measure boiling temperature, vapor pressure, and heating value correlates to the heat of combustion. So now that you've completed your biodiesel analysis and you can measure your heat of combustion, you can compare it to the heating value that you see here. Now, whether you're going to compare it to the higher or lower value and BTUs per gallon or BTUs per pound, I'll let you figure that out. There's a little bit more guidance there in the project itself. Sorry, I got too many tabs open. In the project itself here, it talks a little bit more in number 6 about what those heating values mean. And then the rest of um, the questions are kind of research questions, questions for you to think about, to look up, and to answer that way. So they won't require specific evidence from lab, and they're things that you can put in your own words or you can research and cite there. So that should be good for the biodiesel project. Again, it is pretty big. It's a lot of work, especially with the calculations. So I know I've heard from some of you who've started on the calculations and maybe need a little bit of help. Yeah, the earlier you start on it, the easier it is to get that help. Please don't save it until the last possible day, whatever, a week from Sunday. Start working on it this week, and then if you need to finish a couple things up next week, that's fine too. And yeah, and let me know if you have questions. All right, I also want to get started on the greenhouse gas activity for this week. So you'll see that here. And for this one, you can work your way through the questions here with some help from some of these links, but I wanted to mention a few things also while we're here. So the first thing is, when we talk about greenhouse gases, we're talking about a specific type of light that is absorbed and reflected by these molecules, and that's known as infrared light or infrared radiation. Excuse me. So infrared radiation, radiation just means the emission of energy. We think of radiation often as kind of a scary word in like nuclear radiation or something like that, but radiation, all light is radiation. So visible light, all these different types of light. And there's a spectrum of the different types of light that you can see here on the site, going from the very long wavelength, low energy light, which we call radio waves. And then as we work our way up in frequency, we get microwaves. So we now have shorter wavelengths, longer frequencies. We have infrared. We have visible light. That's light we can see. Ultraviolet light. And now once we get above the visible, we start to get what we call ionizing radiation, which is radiation that is strong enough to knock electrons off of things. So that's where we start dealing with some potentially dangerous radiation. Ultraviolet light, we know, can mess with our skin and give burns, right, or cause cancer, stuff like that. And then X-rays, gamma rays, cosmic rays, stuff like these super high energy types of radiation. But with this one, we're going to focus here down on the infrared light. Infrared light, you can see that has to do with heat often. If you have ever used night vision goggles or you've seen some of those like heat maps, that's because most, anything that is at a particular temperature can give off a particular amount of infrared light. And so you can use infrared light as a proxy for heat. For example, if you ever have like a fire, like a campfire or a backyard fire or something, if you look directly at the flame, you can feel the heat on your face a lot more than if you look away. And a lot of that heat that's hitting your face is actually the infrared light coming off of the fire. So it's not just that the fire is hot and the heat is diffusing through the air, it's that it's giving off that infrared light that's radiating toward your face. So that's something about what happens here as well. And we can measure infrared light via something called an infrared spectrophotometer. And we can get an infrared spectrum that tells us how these different molecules absorb infrared light. So I'm going to launch this visualization here. See if I can get it to work. Yep, there it is. Okay. So what we see here is what we call an infrared spectrum. So the x-axis is different types of infrared light, and then the y-axis is the relative intensity of that light. So if we take a molecule like water, I'm just going to actually flip through these here so you can see some of the different ones. They can get overlaid. We can also turn them off. But it's a kind of a weird graph because it's a little bit backwards. So let me turn off some of these. Most graphs we see 0 is at the bottom for the y-axis, and then the rest of the graph, the peaks and things go up from the bottom, like we just saw with the GCMS. With infrared, it's a little bit different because this y-axis is actually a little bit wrong. I think it's I don't know, but it says relative intensity. Usually this is called percent transmittance on the x-axis. And so what you're really seeing here is when we're up at 1 or 100%, that means all of that light is getting through the sample. So imagine you take a little vial of a sample, then you pass this infrared light through it and detect how much is coming out the other side. You vary the wavelength of the light, and some of it is getting absorbed by the sample and not making it through, and other of it is going all the way through. So like in this example for carbon dioxide, we can see if we look at light over in this region around like 3000 wave numbers, we can see that it's all being transmitted. But then in this region around like 1800, or no, sorry, that's around 2400, we can see that it's being absorbed. So the fact that that goes down means that that light is not transmitting through, but is rather being absorbed by the sample. And so that's what we're looking at when we're looking at things that we call greenhouse gases, is how much can they absorb this infrared light. And you can play with some of the different things here and read some of what's going on here. But basically we can see this is the type of light that is being emitted by the Earth. And so then if the molecule is a greenhouse gas, then we would expect it to absorb some of that light. So you can see like CO2 and O3 ozone absorb some of that light rather than allowing it to escape out of space. And as you'll read about in the readings for the week, the greenhouse effect is a really important thing for, like a good thing, in that it makes our planet habitable, because otherwise, if we didn't have the atmosphere doing that, we would lose all of the heat and we would not be able to survive. But the problem now, of course, is too much of these things, too high of concentrations of these gases are getting into the atmosphere and staying there from burning of fossil fuels and some other processes. And that's causing problems, causing the temperature to increase to an unsafe level. So that's how to use some of these things to answer the questions in the lab. I'm just going to switch back. The other site here. Okay. So then the rest of this activity, after you kind of learn some things about what's a greenhouse gas and if you can tell if it is or not, then we're going to practice a little bit of writing some reactions that have to do with greenhouse gases. So for each of these, you have to do 4 things for each one. First, you have to identify which greenhouse gas is involved. So like we'll do the first one together. During respiration by plants and animals, a carbohydrate, glucose, reacts with oxygen to produce water and carbon dioxide. So what greenhouse gas is involved here? Well, as you'll see once you go through the previous part of the activity, water and carbon dioxide are both greenhouse gases. So this produces both water and carbon dioxide. It produces 2 different greenhouse gases. So for A, that's water and carbon dioxide. Then for B, we're going to label this as either a source or a sink for the greenhouse gas. And what that means is, does it produce the greenhouse gas or does it absorb it, get rid of it, use it up? In this one, number 1, let's think about what's happening in the reaction. We've got carbohydrate reacts with oxygen, and then produces water and carbon dioxide. So the water and carbon dioxide, the keyword here is produce. Since those are the things that are produced, this is a source for those greenhouse gases. It is something that produces the greenhouse gases. If water or carbon dioxide were on the left side of the equation, a reactant, then we would say it's a sink. It's absorbing those greenhouse gases. All right, for C, if it's a source, state whether it is anthropogenic, something that comes from human activity, or natural. So I would say in this case, we can say it's pretty natural. All respiration, plants and animals, it's just a thing that happens, and water and carbon dioxide is produced in this process. So that is a natural process, not an anthropogenic process. For an example of an anthropogenic process, if you look down at number let's say 5 here. During combustion of fossil fuels, hydrocarbons such as octane react with oxygen to produce carbon dioxide and water. So in that case, burning fossil fuels, that's an anthropogenic thing. That's something that we do. So that would be an example of an anthropogenic process. And then the final step, D, is writing a balanced chemical equation. So this is practicing some of the skills we learned in the last module. Can you write a balanced chemical equation that represents each of these processes? And that's it. So you do that for each of them. Some of them are a little tricky. Some of them have a couple reactions in it, so you can kind of do both of them, both reactions there, the best you can. And let me know if you have questions on those. And that's the other activity for the week. So you've got this and the biodiesel project really to focus on over this week and then a little bit next week. Then for the last module, which will be the last 2 weeks of class and including exam week, since we won't really have a final exam, we'll be talking about reading research papers, and we'll write a little bit of something and have another quiz on some of these previous concepts. And that's it. Oh, and we'll do one more at-home experiment. And that'll be the end of the class. So after this, there's really not a whole lot left to do. The biodiesel project is really the big focus right now. So make sure that you can go through that. And as always, let me know if you have questions. And I'm sorry I won't get to see you anymore this semester, but I'm glad we had the time that we did, and we'll just keep meeting up online. I guess the other thing is with Wednesdays now, I'm not on campus anymore. I used to have labs on campus on Wednesdays, so I was really unavailable. So that's a good time now if you need me, if you want to meet over the internet on Zoom or WebEx or something like that, get some help. Those are good times for that. So let me know if you want that or if you need that. And otherwise, I will see you on Blackboard. So good night, everybody.